Good morning, my name is Margarete. I work as a technician responsible for LA ICP MS in Institute of Geosciences at Unicamp in Brazil. I'm also finishing my doctoral degree and this work is part of it. I will present the development of a procedure for chemical characterization of iron meteorites by LA ICP MS. Iron meteorites are extraterrestrial material composed basically of iron and nickel alloys with variable nickel contents and minor amounts of cobalt. Mostly, nickel is about 5 to 10%. They can be classified in two ways, structurally and chemically. These two classifications are complementary. Depending on the nickel content and the cooling rate, two metallic phases are normally present, kamacite and taenite, and an intermediate state called plessite. The structural classification is macroscopic. When a polished surface is etched with a nitrile solution, the phases are revealed. Here is an example of a etched surface. But the structural classification alone don't say anything about the origin of the iron meteorite. That's why chemical classification is important. Chemical classification uses mainly the elements nickel, cobalt, gallium, germanium, and iridium to group iron meteorites in 13 chemical classes genetically correlated. Other trace elements are used for more advanced interpretations. Then, the measurement of these elements is fundamental to the study of known and new iron meteorites. To illustrate the chemical classes, here are shown nickel against gallium and iridium diagrams where it is possible to observe well-defined fields for each chemical class. Then, after chemical analysis, the composition of unknown samples are plotted in diagrams like this to find which class the samples belongs. When the focus is chemical characterization, we have major and minor elements, in this case iron, nickel, and cobalt, easily measured by EDS or EPMA. In the case of trace elements, for decades, the preferred analytical technique to chemically characterize iron meteorites has been INAA. However, this technique is notably time-consuming and its availability is limited. ICP MS has been used for the chemical characterization of iron meteorites in solution mode directly or after matrix separation to avoid interferences. The dissolution and separation procedures is also time-consuming and susceptible to contamination. The use of LA-ICP-MS for in situ solid sample is a fast, direct, and accessible alternative almost without sample preparation. In both cases, ICP-MS is remarkably faster than INAA, presents multi-elementary capability, and adequate detection limits. The main objective of this work was to develop a standalone procedure for chemical classification of iron meteorites by LA-ICP MS. The main analytical challenges was to deal with matrix effects and to find a homogeneous reference material and an adequate internal standard. Our instrumental setup consisted in ablation the iron meteorites with a laser ablation system model Excite 193 coupled to a sector field ICP MS element XR, operating in low-resolution mode for the acquisition of 18 isotopes. All data reduction were performed using iolite version 4. The sample preparation is very simple. It consists in prepare a iron meteorite slice in epoxy mounts and polish them. These are the known and new samples used in this work. To deal with the analytical challenges, we used a new data reduction scheme called 3D trace elements. This DRS allows including the signals of multiple reference materials for calibration and corrections. We adopted to use NIST 612 together a no-iron meteorite called North Chile to calibration. In our case, this feature was important because NIST 612 has low mass fractions for some important trace elements as iridium, osmium, palladium, platinum, rhodium, and ruthenium, while North Chile presents high values for these elements. To allow the use of so different materials to construct a calibration, we applied the yield normalization feature for calibrantes. This procedure corrects for different matrix effects in the different calibrantes. Because of matrix similarity with unknown samples, North Chile was defined as the main calibrant and used as the affinity reference for samples. Time-resolved interpolation generates calibration surfaces instead of calibration curves, as shown in this picture. Another challenge concerning iron meteorites is their natural heterogeneity. It's difficult to define and use an element as internal standard. To solve this problem, we applied the sum normalization option to 100% for iron plus nickel plus cobalt mass fractions. With this approach, we improve the matrix effect corrections without the previous knowledge of the mass fraction of any element as the traditional internal standard approach. This feature allowed the successful analysis of iron meteorites and is mandatory when acquiring elemental maps. Our analytical sequence was planned to construct calibration blocks formed by NIST 612 and North Chile. The time-resolved blocks interpolation generates calibration surfaces that are applied for the calculation of unknown samples. The calibration blocks are repeated each 10 unknown sample spots, or around each 15 minutes. We adopted the mean of 10 spots for unknown samples. Using our procedure, in around 20 minutes we obtain a chemical characterization of a unknown sample, including standards. The validation of the procedure was performed in 2 steps. In the first, we applied our ICP MS procedure to obtain results in 9 no-iron meteorites. In the second step, we analyzed 3 new Brazilian iron meteorites using our procedure and sent these samples to be analyzed in solution mode by ICP MS after chromatographic separation at Alberta University. Here we present a comparison overview between results obtained by ICP MS and published data for the 9 no-iron meteorites. The relative difference between obtained and published values is in the range of more or less 20% for almost all elements and samples, which is an acceptable accuracy for trace elements level. The first difficulty to validation was that there is few published values and no information about uncertainties. Each element with published values can be individually evaluated. The plots of obtained values versus published values result in a trend line with a slope and error correlations near to the unity. We plotted the obtained and published composition for the 9 studied iron meteorites on classical chemical classification diagrams and can affirm that our results lead to the same existing chemical classification for the analyzed materials, and therefore our procedure is fit for purpose. The second validation was performed by the comparison between LA-ICP MS obtained data and ICP MS results obtained in solution mode after chromatographic separation of iron for 3 new Brazilian iron meteorites. The results obtained by both methods are in agreement for 2 samples, Conceição do Tocantins and Nova Olinda, as presented in the graphics. Plotting the obtained results and the diagrams for chemical classification of iron meteorites, we were able to classify Conceição do Tocantins and Nova Olinda as 2AB class, as shown here. But the third new Brazilian iron meteorite, called Augusto Pestana, presented high RSD values for the 10 spots and disagreement with ICP MS in solution mode. To investigate the reason for the observed differences, we etched the polished surface with a nitrile solution to reveal the presence of different phases. The etching process revealed a dark phase corresponded to kamacite, contrasting with a clear plecitic domain. Polished and etched surfaces showed that the aleatory ablation spots were distributed in both phases, explaining the high discrepancies among spots. The mean value obtained for the red circles and the blue squares resulted in RSD minor than 20%, and the results obtained in kamacite phase is in agreement with solution mode. Using this sample as a study of case, we explored elemental mapping using LA-ICP MS for chemical classification of iron meteorites. We selected this area containing both kamacite and pleicite phases for evaluation. In this experiment, we adopted the same approach for data reduction used for spot analysis. The raw analytical sequence took about 1 hour. The obtained composition maps of the measured areas clearly reproduced the differences between kamacite and pleicite and agree with the mass fractions obtained by spot analysis, consider the uncertainties. Using a software tool, we selected a region of interest to calculate the local elemental mass fractions. The comparison between the obtained results over the integrated area with previous obtained spot analysis are in agreement, showing that both approaches provide similar data and the same chemical classification. As main conclusions, we have that LA-ICP MS is a fast and accessible procedure for iron meteorites chemical classification, and we have overcome the following analytical challenges. And the first is the lack of homogeneous and well-characterized reference materials for external calibration. Then, after applied yield corrections for each element in NIST 612, we were able to use it together with North Chile to construct 3D calibration surface and calculate mass fractions in iron meteorites. The second, that the knowledge of a homogeneous matrix element to be used as an internal standard. Then we implemented a sum normalization approach, considering iron plus nickel plus cobalt equals 100%. In this way, we do not need to have a previous analysis of any elements by another technique, and matrix heterogeneities are automatically considered. And in the third, The natural heterogeneity of iron meteorites unknown samples. Acquiring an elemental map by ICP MS was possible to check the presence of heterogeneities and at the same time use the obtained mass fractions data to reach the chemical classification of the iron meteorites, choosing the appropriate area. Thank you.